Lab 4, Spring Oscillation. Introduction. The goal of this lab is to depict an ideal spring mass oscillation system by using the computer program Python. We were given a video to analyze and tracker, and then we were given the goal to mimic this through our computer-generated model. The questions we were asked to keep in mind during this lab were, is the energy principle satisfied, and how do the periods of oscillation in the x and y axes differ? The equations from the momentum principle are Vf is equal to Vi plus F net over m times delta t. The position final is equal to position initial plus velocity final times delta t, and then the force of gravity is mg times 0, negative 1, 0, and the force of spring is the spring constant times the displacement of the spring times L hat. From the energy principle, we have kinetic energy is 1/2 mv squared. The gravitational potential energy is mass times gravity times height. Spring potential energy is 1/2 times the spring constant times the displacement of the spring squared, and then energy total is equal to the sum of the kinetic energy, the gravitational potential energy, and the spring energy. From tracker, we chose our axes to start at where the spring connects to the wall, and in the beginning of the video, we had the spring length being 0.7 to where the mass was resting, and then he picked it up, and we chose these frames. So for the part 1 of the glow script, I put in that the ball's mass was 0.402 kilograms. The ball's initial position was negative 0.119 meters in the x direction and negative 0.619 meters in the y direction. And then for the constants, we have g is 9.8, the spring constant is 6.83, and the relaxed length of the spring is 1.2 or 0.123, sorry. And that L is ball position minus spring position. L hat is L over magnitude of L, which gives us a unit vector. And the displacement of the spring is the magnitude of L minus L naught. And then for the energies, we have the energy is 1/2 mv squared for kinetic. The gravitational potential energy is the ball mass times gravity times ball position y, which is the height. And then the spring potential energy is 1/2 ks squared. Then total energy is the sum of all three. For the last part of the glow script, we have that the force of gravity is mg times the negative 1 vector, which puts it in the negative y direction. The force of the spring is negative ks times L hat times s, and the net force is the sum of these two. Then from the momentum principle, we have that the ball velocity is equal to the velocity plus the net force over the mass times the change in time, and that the ball's final position is equal to the initial position plus velocity times time. So this is it when it's run with the data from tracker. And as you can see, the total energy is staying constant because it's the sum of all three. And as the potential energy due to gravity goes up, the spring energy goes down, and the velocity is and as you can see, the blue ball is following right behind the red ball, and the red ball is the experimental data. So this is the energy graph. You can see that the total energy is staying constant at 0, and that the velocity is going between a minimum and a maximum, and that when the spring energy is high, the gravitational potential energy is low, and vice versa. Here we have the model versus experimental data from the x and y positions. So in the y graph, you can see that the experimental does not reach as far up or as far down as the model, and this is because in the experimental version of this, there is friction and the mass of the spring, which has inertia and is part of the force is given that to move. And this is also seen in the x direction, but not as much because gravity really makes it apparent with the inertia of the spring. So what does it mean? The energy principle is satisfied in the model. Since the chosen system is the Earth, the spring, and the mass, the sum of all the energies is constant, and this can be seen by the total energy bar having 0 change in the graph. For the plots of motion in the x and the y axes, I can predict that the x-axis period would be about 1.6 seconds, and in the y-axis it would be 1.6 seconds as well. These estimates are about the same, and this makes sense due to the symmetry of the motion at hand.